I'm Blaine Mooers. I'm an associate professor of biochemistry and molecular biology at the University of Oklahoma Health Sciences Center in Oklahoma City. I'm developing a library of code fragments, or snippets, to ease the use of PyMOL, a powerful molecular graphics program for viewing the molecular structures of proteins and nucleic acids. I'll introduce PyMOL and the nature of snippets, and then I'll demonstrate the use of the snippet library in a Jupyter notebook using Jupyter Lab. This slide shows the workflow in my laboratory. We use X-ray crystallography to determine the atomic structures of proteins and nucleic acids from the RNA editing system in trypanosomes. We also work with several colleagues on proteins important in cancer, such as the one shown in the lower left. With purified protein, we grow crystals. This is a large crystal, probably 0.7 millimeters in length. It's mounted in a cryo loop and put in a cold stream at minus 173 degrees Celsius. This enables the crystal to continue to refract for a long time when we're shooting it with X-rays. Some X-rays are diffracted, and we wind up collecting these diffraction spots using a image detector shown here. The spots are collected as the crystal is rotated. We have to do this for, on average, 180 degrees. We then process the data and take an inverse Fourier transform of the diffraction data to obtain an electron density map. We fit a model of the protein to that map. One contour level is being shown as this chicken wire mesh. So looking at proteins on the top and bottom, and then in the middle, you're looking at a drug molecule that is binding to the ATP binding site of this protein tyrosine kinase. In the lower right, we have compared two structures with different drugs bound, and we're examining how steric effects may inhibit the binding of drugs to a mutant of this protein. So figures like this that are made in PyMOL are often used to illustrate scientific papers about structures. PyMOL is also popular for the purpose of making cover artwork. Here are some examples of molecular structures made in PyMOL on the covers of several leading scientific journals. PyMOL's popularity is reflected in this graph. This is a result of a poll that's been running for about a decade at the Rosetta Design Group website. There are actually about 25 molecular graphics programs that have been nominated. PyMOL has been sitting at 38% for several years. PyMOL was developed by Warren Delano, who's shown here at an open source software conference in 2005. He started work on PyMOL in the early 1990s while he was an undergraduate student in computer science and molecular biophysics at Yale University. At the time, he was working in the laboratory of Axel Brunger, a leading protein crystallographer, worked on the development of the crystallographic software known as Explorer, which has since evolved into the program known as CNS, which still is in use today. He earned his PhD in protein engineering with Robert Wells at the University of California, San Francisco. In his spare time, he continued to develop PyMOL. He took a postdoc position with Robert Wells and likewise continued to develop PyMOL in his spare time. In 2001, he released PyMOL. In 2002, he left his postdoc position to start a company called Delano Scientific to further development of PyMOL. Unfortunately, he died in 2009. His widow made arrangements with Schrödinger Incorporated to distribute PyMOL and to continue its maintenance. Schrödinger Incorporated develops proprietary drug design software. In addition, arrangements were made to set up a Warren Delano PyMOL open source fellowship, a link to which is at the bottom. I won one of these fellowships in 2018 to develop a library of snippets for the PyMOL macrolang. This has been developed for about 18 leading text editors. Support for snippets has become widely available in text editors over the past. This is animation, the use of a tab trigger that's called 3 maps. That's mapped to 12 lines of code that generate 3 contours of electron density. The text editor that's being used is Visual Studio Code. The nice thing about Visual Studio Code is that it provides a auto-completion of the snippet name, and it also provides a preview of the snippet along with a description of what the snippet is. As soon after entering the appropriate snippet name, you hit Tab. Tab leads to that action leads to the insertion of the code. So the preview allows you to ascertain whether or not that's the right snippet. And then you can see these highlighted areas. The cursor will advance to the first so-called tab stop. This is some coding that's hidden and not shown to the viewer that controls the movements of the. So while 4DGR is highlighted, we can start typing over that default value, and we can replace it with a different name, or we can just hit Tab again to advance to the next tab stop. So the tab stops that have identical parameter values are mirrored. So you can see the 4 are highlighted. And we're going to change glycan to sugar in this example. So this ensures that all 4 sites are edited. So one problem with the editing of code templates or snippets is a failure to edit all the sites that need to be changed. That can lead to bugs and time wasted on debugging. Okay, and then it will advance to the next tab stop. This is the GUI for PyMOL. The area, the viewport in the lower left allows one to interact with the molecule by using the mouse. You can change the orientation by using the computer mouse or trackpad. Multiple models can be uploaded. Each model shows up as a tab or entry in this internal GUI. Each of these entries has 5 pull-down menus available. And so in this case, I selected A, and under A, I selected preset, and then under preset, I've selected publication. So a series of parameter settings have been set up to give a rendering of the atomic coordinates in this fashion. The default display normally would be just a display of the structure as sticks, with the sticks representing bonds between the atoms. So the raw data are just the atomic coordinates of the atom. And these parameter settings allow the generation of these fancy renderings. So in this case, we have a fancy alpha helix in which the interior of the alpha helix has been colored gray. There are additional cascading pull-down menus across the top, and we'll return to one of these later. In addition, then below this window is the command history window. You can copy commands out of this window and paste them on at the PyMOL prompt. The PyMOL prompt will take commands that are both written in the PyMOL macro language as well as in Python. PyMOL is written in C due to the need for speed in the manipulation of the molecule, but it's wrapped in Python to ease its use by users. And then that, in addition, there's a PyMOL macro language, which has a much simpler syntax than Python, and much easier for non-programmers to use. These are the default molecular representations in PyMOL. Upper left, we have lines in which the bonds connecting atoms represented as points are shown. The atoms are colored by their element type, so carbon is colored green, although it can be colored any color, whereas oxygens are red, nitrogens are blue, sulfurs are yellow. So in this case, the stick representation has the lines replaced with thicker lines, and the carbons here have been colored yellow. Here the carbons have been colored cyan. Here they've been colored magenta. The spheres represent a representation in which the van der Waals radius of a particular element is used to generate a sphere. So these spheres are centered on the atomic positions of every atom. If you roll a ball that has the diameter of a water molecule across this van der Waals surface, you'll generate a molecular surface, which is quite smooth. Here's a molecular surface generated as a mesh, And then here's the van der Waals spheres represented as dots. Another kind of representation is that it helps to visualize secondary structure elements is to simply connect the C alpha carbon atoms that are at the center of every amino acid. And so we'll just have one atom represented here for each amino acid. And this is highlighting two beta strands. Then on the lower right, we have what's called a cartoon in PyMOL, or a ribbon diagram normally. It shows two beta strands as returning to the pull-down menu. So now I want to return to the setting pull-down menu. We're going to go to Edit All. Well, we obtain this menu. We can enter on this line the start of the name of a parameter to bring it up. You have access to over 600 parameters. PyMOL has about 500 commands and over 600 parameters. This vast array of commands and parameters allow you to exhibit exquisite control over the appearance of the molecule, and this is a source of the popularity of PyMOL. However, setting these values is only temporary. There's, of course, and if you have to set a large number of them, you're not going to have a record of your work. So it's prudent to instead use a script file to store such values. It's quite common to have to set several dozen parameters to generate a publication quality figure. So here's an example of a script file written in the PyMOL macro language. This is for a snippet that's involved in generating grayscale. This is actually quite a long snippet, several hundred lines long. It's involved in applying grayscale to a figure for the purpose of producing a figure for maybe a low-budget book chapter. Such an option is not available directly in PyMOL. So the commands are shown in orange, the parameters are shown in blue, and the parameter values are shown in red. This image shows the ambient occlusion being applied to a short double-stranded RNA helix. So on the left, result of entering the AO tab trigger. In the middle, we've entered the AO-BW tab trigger. And we've gotten the effect on the left applied in grayscale. And then on the right is a variant in which the carbons have been colored black. These capital letters above are actually mapped to Python functions. So these can be applied in an interactive session. You don't have to use a script file necessarily to use these. They're available at this website. However, if you have loaded these PyMOL shortcuts up and they're always present when you start up PyMOL, you can include AO in a PML script and it'll be applied. Well, the problem with the PyMOL macro language, even though the syntax is pretty simple, the commands are so numerous, it's hard to remember their names. So many of us suffer from the forgetting curve. Our memory of the commands falls with our time since our last PyMOL session. Many of us use PyMOL on an episodic basis when we're preparing images for papers and grant applications, perhaps every several months. So our probability of recall is going to be quite low. Hermann Ebbinghaus is the person who quantified the forgetting curve. He published his work in 1885. So the primary reason for developing the snippet library is to overcome this poor recall of the commands amongst people who are infrequent users of PyMOL, which is the vast majority of users. PyMOL has over 100,000 users, most of whom are not computer programmers. The second reason is to help students develop the habit of using scripts. So generally, I suggest that students start off by using the shortcuts in that shortcut file, and then they can migrate to writing scripts. The snippet library will speed up the assembly of the PML scripts. Because of the tab stops, this can reduce the time spent debugging. In addition, the snippet library has highlights unfamiliar features of PyMOL, so it can help users learn about the dark corners of PyMOL. In addition, the snippet libraries you've already seen with ambient occlusion can extend what can be done in PyMOL. And then finally, I think PyMOL can help with two fears. You've heard of FOMO, fear of missing out. Well, there's FOCL, the fear of the command line, and the fear of writing scripts, FOSS. These are two widespread fears amongst molecular biologists. So what about running PyMOL in Jupyter? In the ideal world, we would have the viewport available to us in a output cell where we could interactively, where we could issue commands from a code cell and have the output show up in the output. However, this is not possible right now. There are two packages available that allow interactive viewing of macromolecules in Jupyter. One's called NGL View, and the other one's Bio 3D View. Another option is to have PyMOL open and the Jupyter Notebook open, and then you're to have launched PyMOL as a remote procedure call server. Then you can send commands from PyMOL, from the Jupyter Notebook to PyMOL. And there's a number of these receivers have been developed. However, I find that they often break with the frequent updates of PyMOL. So PyMOL is updated about once every 4 months. Another option is simply to live with working with the static views in the Jupyter Notebook and to run PyMOL via the PyMOL API, which has just become available. So if you have installed a kernel that is mapped to the Python interpreter side of PyMOL, you can import the CMD module from PyMOL, which provides access to about 500 commands. So in order to run PyMOL on a Jupyter Notebook, I'm going to use Jupyter Lab, the Jupyter Lab Snippets, multi-snippets extension for Jupyter Lab. Included this snippet library called PyMOL pysnips, which has the PyMOL code rewritten in Python, because at present you can't send the PyMOL macro language code from Jupyter Notebook to. Now I've included snippets in this library that provide for the imports that are needed. So we need this command module, and then we need these two imports from IPython in order to load up an image from disk. And then I've provided a path where the images will be stored. So for this test case, we're going to apply a script that will display a tRNA molecule shown down here with the bases replaced with rectangular blocks. Purines are the long rectangular blocks, and the pyrimidines are shown as a square rectangular block. This script is a wrapper around the DSSR program. So the great thing about the multi-menu extension is that it's very easy to create menus simply by creating folders within the Jupyter library. And the name of the menu is the name of the folder, and then you have subfolders in this folder, which provide submenus. And then, so under nucleic acids, we actually have about 8 snippets. We're going to select the first snippet, and this is the corresponding code. In single quotes, you can see the PML code. You can see the cmd.do. So the do function will convert the PML code. We'll send the PML code with PyMOL. So after doing that, we get the PNG file written to our disk, but we need to load that. So under imports, we'll import IPython.display to get the code that we need. So we need this function to load a PNG file. So here's the corresponding PNG file. As just a side note, I made the file originally with 160 by 160 pixels, but to fit this notebook well, I had to reduce the size to 500 by 500. However, the disadvantage of this approach is that of that library is that there aren't any tab stops nor tab triggers. So to compensate for that, I made a second library, and in this library, the code has been placed in a comment, and the corresponding metadata required for the tab stops is shown here. So the idea is you can use your eye to guide yourself manually through these and to ensure that you edit all the sites that you need to. Of course, when you're done with this, you could always delete this comment. Then below, I've also provided a description and the source. So my recommendations for the use of snippets in Jupyter are for the developers to add support for tab triggers with autocompletion like we saw in Visual Studio Code. I highly recommend the use of camel case in the writing of the tab trigger names. It is the standard, of course, in Python to use snake case with underscores between the names and our words in lowercase. The problem with that is that underscores are hard to reach on the keyboard. It's more ergonomic to use camel case. And since you may be entering snippets quite often, it would be beneficial to stick with camel. The menu labels should also include these tab trigger names. Support for tab stops should be provided and these tab stops should have the capability of being mirrored, such that a change at one is propagated to the others. And finally, the snippets should be stored in a simple format. So some of the existing extensions store snippets in JSON files. That's not very user-friendly. So more user-friendly formats can be found in Ultisnips for Vim or Snippets for Emacs. So in summary, snippet libraries can ease the building of PyMOL scripts. The tab triggers and tab stops are needed in Jupyter, and snippets can support literate programming with PyMOL in Jupyter. I'd like to acknowledge Thomas Holder. He's the lead developer of PyMOL at Schrödinger Incorporated. He administered my fellowship, which I had to submit 4 quarterly reports, and he handled that. I'd like to thank Miranda Brown, a rotation student in my lab, who wrote the documentation found on the GitHub site for this project. Also like to thank the OUHSC Python workshop, to whom I presented some of this work. And finally, I'd like to thank the fellowship and these sources of funding for the support of my salary.